to start with a new topic. It is a new architecture, different from what we have been dealing with so far. It is called a convolutional neural network. The convolutional neural network, they use a concept which is almost like a mathematical concept of convolution, almost like that. Convolutional neural networks. Just as an aside, if you remember, what have we been dealing with? We have been dealing with hidden layers, right? And then another set of hidden layers in which every one of these is connected to every of them, right? If you remember, we do from this, I don't know, I'm just trying to make all of this interconnects. By now you see that this is a mess. This is a very, very densely, the word is densely connected. Right? So when you take a layer, how many layers did I take? Just 5 and 5. And you can see that there are lots of, let's simply use the word lots of interconnects. Each interconnect has a weight parameter. The weight parameter, isn't it? So this region, if you look at it, it looks dense. And then you can imagine another layer, and then that also has a lot of dense connections. And so these sort of networks, they are often called dense neural net or feed-forward network. And if you remember the word in PyTorch, you use forward. Why? Because the input goes X here. It goes through the first layer, produces an activation, goes through the second layer, produces an activation, and it keeps moving forward till you get the final Y hat, the final prediction. So that is why these things are called feed-forward network. This is a synonym for it. And the classic pictures of neural nets that we see in our mind, you see all of these dense interconnects between them. The problem is evident from this picture. The main problem that you see here is there's so many parameters. Can you imagine that if you make a dense layer that has, let's say 1,000 nodes, and it is connecting to the next hidden layer, which has 1,000 nodes, you're suddenly looking at 1 million parameters just off the bat. Just between these two hidden layers, you have now 1 million parameters. This becomes really problematic when you start dealing with complex objects like sound, like images, and so forth. So we'll take an example of an image. Let's say that you have, these days when you take an image, what is the size of an image? Right? Quite often your images can be 128 by 128 minimum, like, or maybe like 256 pixel. If you look at the typical image that you take on the internet or something like that, let's say 256 cross 256. And then there are the 3 RGB channels, red, green, blue channels. So what it means is it is a grid of, it is actually a grid of 3 grids, 3 layers, and each grid layer, let's say this is the red, has 256 and 256. And there is some integer value, let's say, sitting there. Let's say 4 is sitting here, like 11 is sitting here, and so forth. This is how the data presents itself. This is how you store images, or that's how you visualize images. But now imagine that you're feeding this into a neural network, our dense network. The first thing we'll have to do is we'll have to flatten it, this, into an input vector. Isn't it? So how would you flatten it? You could read it literally row by row, right? Row by row by row by row. You could read the data, and then you could go from red to green to blue channel. So you would end up with 256 times 256 times 3. If one of you wants to do the mathematics, Could somebody tell me what number it comes out to be?
About 2 megapixels. 196,608.
196,608. So let us say 200K, right? Approximately 200K, right? And now let us say that you try to feed it into a neural network. When you see this vast number of parameters, let us say that you feed it into a deep neural network. A first input layer is the first hidden layer. So hidden layers are often called fully connected layers, right? For the reason that everything is interconnected to everything else. So you will see this terminology all over the literature now, fully connected layer, right? People also call it synonymously a dense layer for reasons that we just talked about. And then, because these are feed forward layers, or data linearly moves forward, like they are also called linear layers, right? So for example, you see this literature, if you're doing TensorFlow or PyTorch, they use the word dense. If you are doing TensorFlow or Keras, TF Keras, they use the word dense in the library. And if you look at PyTorch, it uses the word linear, right? And if you go back and look at the code, when we build our neural networks, we put all these linear layers together. So let us say that we create a linear layer of a modest 1024 nodes, which are 512 nodes or whatever you want to pick. You realize that you're multiplying this by 1024. So the number of weights that are there, because each of these things is interconnecting to 1,000, and there are 200K things. So what you end up with is 200 million parameters just reaching the first layer, just in the first layer. And that is when we haven't included the bias. So whatever this number comes to, plus you can include another for bias terms, which is insignificant, but it is there, right? So you realize that you're looking at something in the order of 200 million parameters. And so by the time you feed in a few more layers, you have a whole lot of parameters. So when you have a neural network that has a lot of parameters, or any machine learning model that has a lot of parameters, what could go wrong? Would one of you like to take a stab at it? What possibly could go wrong?
Crash. It will crash.
No, that's a computational thing. Imagine that you're filthy rich and you can afford huge amount of hardware. And I hope you do become that. So
Might just run slowly.
it will run slowly, that's one. See, there is a more...
It might not converge.
Yes.
Yes, see, data point. Think of how many data points you need to train a model like this. We are talking of hundreds of millions of parameters. When you have hundreds of millions of parameters in a model, you need a vast quantity of data for it to learn properly, for it to get properly trained. Right? So it will tend to have problems of overfitting because lots of models will overfit. Right? And in terms of the visualizations that you saw, what you will end up with is a lost landscape that has a lot of non-convexities, and God knows where you'll get stuck if you just run a few hundred iterations or 1,000 iterations. Right? So it gets hard to train these things. So then comes an idea, how do we deal with this? This idea actually dates back to the 90s, and it comes from researching, it comes from neurobiology and neuroscience of cat brain. People studied how a cat looks at an image. Whenever I think of it, somehow it creates very rather cruel pictures in my mind, how they must have figured it out by putting all sorts of electrodes in a cat or whatever they did. But the fact of the matter is that they found that when you look at an image, when the cat eye looks at an image, and can I just imagine that this is the cat brain, this is the cat body, this is a cat, right? So let's say that this is a cat eye. It it is looking at something. It's looking at an image of a tree, let us say. And there is a squirrel here that it is interested in. So then what you notice is this part lights up one area of the brain. This part lights another area of the brain. And different parts are lighting up different areas of the brain. The entire image, actually, you can think of it as a plane here, some sort of a imaginary plane here. And as it looks at this picture, different parts of the plane light up and they respond to different parts of the image. Have you got it? And so that inspired a different architecture that is quite interesting actually, and widely used when you think of self-driven cars and whatnot. And this, it all begins with this. So let us build the idea. So guys, are you getting the main idea? That there is a spatial orientation. Which part of the brain responds to which, there's a mapping. This part of the image is being responded to by this part of the brain. Are we getting that? As simple as that. Right? So you can almost imagine that this image is being projected somewhere in a conceptual sense. Imagine that there is a screen in the back of the cat's brain, and this image is basically being projected there. So each little piece, this squirrel is activating here, and this little thing, whatever it is activating here, and things like that. Okay. So based on that intuition, we created an architecture. But it needs the notion of something called convolution. Now, convolution is an interesting concept, and it's a mathematical concept. I will give you the formula, but I'll deliberately give it to you in a wrong form. The reason is the way we use it in neural networks, we use what mathematicians would say, not exactly the right thing, not the strictly correct correlation. It is a slightly modified or a simpler version of it. It is in some sense slightly wrong, but we use it in deep learning because it really doesn't matter. There's no difference in using the right form and the wrong form. And the wrong form is more intuitive and faster, and it just saves us a couple of operations. It doesn't matter basically. Okay? So what it says is that it is this, the convolution of a function. So suppose you have a function, which is this. Right? The convolution of this with some other function is this. So imagine that there is some other function g, and that other function, I will say, is like this. Let's say that this is gx. And let me write f in a more way. Something like this. This is fx. And this is gx. What it does is, when you multiply these two things together, you will realize what will happen. This is the peak of g. So this area of f will contribute a lot more. The product of these two will be much more than the product of g with respect to this or this, isn't it? Do you see my point, guys? G is stronger here. So this point is not as shining bright as far as this convolution product is concerned. If I look at A, B, C, look at A. G at A is just this much. Let me just call it G of A. A, B, C. And G of C is also small. Right? G of C is small. But G of B is pretty big. So when you multiply this function with this, what will happen is, do you realize that beyond a certain value, this function is essentially zero? So you can imagine that this result that you get is result will have effect only in this area, more or less, right? It will, this area a little bit in, this part, how should I say it? Only, the major parts are here. So only this little part of fx will get highlighted. Am I making my idea clear, guys? Right? So I'll give you an intuition of what it is, which is a very physical intuition. So imagine that you have a torch. The torch is casting a light. Here is the torch, and it is casting a glow, and the glow is, the intensity of the glow is like this. If you were to measure the intensity of the glow, then you would agree that it is very sharp here and less here, right? If you are measuring the intensity of this glow. Am I making myself clear, guys? It will be very sharp in the center, very bright in the center. This is the light of the torch coming through. And you're measuring on a screen. You're measuring on a screen. You would agree that it would be brightest here in the center and taper off gradually as you move away from it. Is this idea of a torch easy to understand, guys? Just pick a torch and shine a light on the wall. You notice that it has a focus light and then gradually it thins out from there. Did we get that intuition?
Yes, sir.
So now imagine that this intensity pattern, if it was one dimension, is your g of x. So what happens? If you think of your function as a wire hanging out there, so imagine that you have, let me use a different color for this function. Suppose you have some function, right? And you use your gx. So suppose you focus your spotlight at this point. The same thing, if you have your gx shining light here, this is your gx, and this is your fx. Now tell me what will be the product? The product of fx times gx. What will it be? It will be very little of this. So if I have to write it in red color now, you would say wherever this peak is, this value, it will really shine through, right? It will be thick. Then as you move away, the light will thin out, right? Another way of saying it is that in some sense, what you're seeing is only this little bit. This little bit is visible. This little bit is visible. Yes. Yes. Isn't it? So the convolution of this, which is this integration, forget the integral, basically think it's multiplying it together. It is essentially shining light on a little bit of that function, probing it. That's why you often call this the probes. Gx is the probe. Right? It probes it, the function, at a specific point. And now imagine that you're taking your torch and you're moving your gx back and forth. Right? So suppose there is a translation parameter here, gx minus theta. And as you increase theta, what happens? Different parts of it keep getting highlighted. Right? Do we agree with that? That as you move your gx from here to here to here to here to here, all these little bits of the wire you get to see, of the function you get to see.
It's a little bit off screen.
What's that?
The function is a little bit at the very bottom of the screen.
Oh, okay.
It's a little bit off.
Center.
Oh, yes.
So what we are saying is that this gx acts as a torch that shines light on bits of the function everywhere. To do so, and just to take the, in some sense, some accumulated, like you say that total, somehow aggregate this value, right, is to take the integral, right? And we won't go into that part. So the definition of the functional, and this also, by the way, is not correct. So you say that at this particular value of theta, the conv of x at theta, or I don't know, you can, I think I'm mixing up my notation, but just forgive me for that. If fx gx minus theta means at theta, at this point, theta, right? What is it? At this particular point, at point theta, let's say it will just be a function of theta, this location, what is visible? Intuition would be what is visible? What is the sum total of everything visible? And so now let's relate this idea back to that cat. So again, to recap, we had a cat, and there's a tree, and there is a squirrel, and so forth. And there is a cat looking at this squirrel. And then in the back of the cat's brain is a plane in some sense, right? And let's give it a tail also. There we go. And this little cat is staring at the picture. So you would imagine that it is as though this area of the brain, it is ignoring the entire screen, but it is shining a torch only at one region of the scene. Does that intuition make sense, guys?
Yes.
This area, so it is almost as though this has a gx, right? And you can have the theta parameter to move it back and forth, but let's forget that. We'll be sloppy in our notation. So this is shining a light here. This region is shining a light here. So shining a light and observing different areas of it, mathematically, it is the same in the mathematical language of it is you're convoluting the scene with a filter. What you have, this torch, the formal word of the formal name that people use in the literature is, they often call it, I call it torch, but people don't call it torch. So you won't find the word torch in the books, this intuition. You'll find the word filter or kernel. These are filters of kernels. And in a way, you can relate to the word filter. So what this filter does is it will filter and look at only one region of the landscape. Right? So what you do is you convolute, use different areas, different regions are convoluting, or they are convoluting across different scenes, are shining light across different scenes, or different parts of the scene. Right? So once we get that intuition into us, now actually convolutional neural networks become absolutely obvious. We just try to reproduce that in a computer, in a deep learning architecture. And literally that's exactly what we do. So, well, in this world, computer science is discrete, right? So what we do is, let's say that we are looking at a scene, right? First imagine that the scene is, I'll just draw the scene out, right? Then I'll write it in numbers. Let's say that the scene is, there is a shift from black to white. Are we together? And then there is also, just for fun, let's say that this is white. And just for fun, let us imagine that there is another diagonal black line going across. So these are colored regions. These are colored regions. I'll just take a very simple scene. And now let's see how would we detect it. So what we do is we take, so this scene would be a bunch of numbers. So blacks are usually, let's say that, I'll just simplify it in a very simple way as 5 by 5 by 5. So imagine that this scene is written by 5 pixels by 5 pixels, 1, 2, 3, 4, 5. So what will happen is blacks will have values close to 0, 0, 0, 0, 0, 0, 0. White will have values close to, let me just say 10, just for the sake of argument. Well, it could be F, but okay, let me just say 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10. And then might as well add a diagonal also of black. So what we do is, let me just draw these lines here. And now might as well nuke out the diagonal ones also. So this is black and this is black, right? Black, so 0, and then this is not 10. Actually, I shouldn't have used 10. I wish I had used something else because 1 and 0 look so similar, 10 and 0 look so similar. Suppose this is 9, right? And this is, let me convert all of these to 9s so we can easily see the difference between the two. 9, 9, 9, 9, 9, 9, 9. So these are pixel strengths. Huh? And let us just look at a grayscale image at this moment, grayscale. So this. So does this look like a good representation, a pixel-wise representation of this particular image, mathematical representation of this image? This is how you save the image in grayscale. Huh? You give it some value. So now let's think, how can we shine the light at places and detect things? Right? So the way you do that is slightly different actually. Cat brain is pretty smart, it can do a lot of things, but we do with very simple ideas. Let us say that we take what is called a filter. And that filter has a property like this. It looks for vertical edges. So let us say that I put 1, maybe 0, this is by the way, this is a cliche. Almost everybody starts out with this example. So I'll also start out with this example, something like this. For some reason, 1, 0, minus 1, 1, 0, minus 1 is pretty common. So this is what you call a filter, right? Or your torch. Right? I think of it as a stencil. You know, for another analogy that I give it is stencil. So, you know, children do this. They'll take a page, right? And suppose you have a V cutout on the page. And you ask the child that on this wall, there is a V, go match it. What will the child do? Suppose this is the wall and somewhere there is a V. Let's say that the sizes match for the sake of the argument. How will the child do it? The child can't see, let's say. All it can do is if these two match, he will know because this is all dark colored, let's say. So his way is, this is a cutout. He can take this page here, see, are you seeing the inside area? Is it all black? Right? So it is not all black. So the child says, no, this is not it, not it, not it, not it. And ultimately the child will end up bringing the filter to this region, to just the right place at which it would have an exact match. You will have an exact match to the stencil. Would you agree? Right? This is how you can just scan all over and you would know that at one location you'll hit it. And then this would match this. Is this intuition clear, guys?
Yes.
Yes.
It's a simple intuition. So this is exactly what you do. This filter or this is a stencil that is deliberately looking for a vertical edge. And let's see how does it do that. What you do is you take this stencil and first you put it here. And this is the convolution part that comes in. Remember I said that the convolution is f, the initial image, fx is the initial image, the actual image times the, well, I shouldn't say the actual image, I shouldn't say filter, because people in this literature, right, use F for filter, right? So let's say that you convolute the original image. Let me call it the original image O. O with this, at this particular location, right? Multiply the two and the integral becomes the summation. So let us do that. What we do is we multiply 1 here with 0 here. So it becomes
Should the window size match the?
Yes, yes. So you notice that 3 by 3. So I just, oh, sorry, you're right. I made a mistake actually. Thank you for pointing out. This is, it should match because this stencil, you're just bringing this stencil, this filter, and putting it here. So let's see what happens. So thanks for correcting that. So now what happens? 0 times 1 is the first row. This would produce 0. 0 times 0 is 0. 9 times minus 1 is minus 9. So we got a positive value. And then once again, you can continue that and you'll realize you'll get another minus 9. Are we together, guys? Right? You add both of these up, minus 18. So what you do is you go and you start building a cell. Here you put minus 18 as your answer, right? Now you take this stencil, you bring it one step below, right? And you would realize that if you bring it one step below, yeah, okay. So you bring it one step below, it will still be minus 18. You bring it one more step below, it will still be minus 18, right? And now you take the stencil and you shift it. Let us say it has gone to this location. Sorry, let me make it wider. Yeah, let's say that the stencil now moves to this location. It is still your 3 by 3 stencil, right? So now what happens is you have shifted it by 1 and you again start multiplying these two. So the first column is 1s multiplied by 0s, you don't get anything. The second column is 990 multiplied by 000, you don't get anything. The third column, you tend to hit a jackpot. You get 999 times minus 1. So you come up with minus 27, right? And now you bring the filter down one level and one more level, you'll realize minus 27, minus 27. Do you agree, guys? Do you see how I got minus 27 here?
Yes.
So Asif, it will be 18, I think, for the next one because there's a 0, right? Oh no, so no, you're right, like minus 27.
So minus, and then you move it one more step in this direction. And now what happens? When you, let me use a different color. So guys, I'm a little bit sloppy, eh? So sometimes I make mistakes. So be on the watch out, I can make mistakes.
So isn't it minus 27, minus 18, minus 18?
Yeah, because there's a 0 in the fourth pair, so it will be minus 18, minus 18.
Here is minus 18, huh?
Yeah.
Minus 18, minus 18. All right, I'll take that. So it means that you guys got it. So now let's look at the green one. 111 multiplied by 990. So you get 18 here, right? So you get 18 plus, well, 9s multiplied by 0, you don't get anything, plus 9s multiplied by this. So that will be minus 27. So 18 minus 27 is minus 9. Do you see that, guys? It's minus 9. And then you bring this filter one step down. I don't know. This 0 is coming in our way, right? It's screwing up our computation. I feel like cheating and putting a 9 there.
No. It's a 0 for that cell.
What happens? So let's think about it. If I bring this here, the filter comes down here. Now you're multiplying 909 with 1. So it means that you'll get 18 once again, plus next column is 0, and the next column here is 990. 990 would be minus 18. So you would get 0 here. And I believe you would similarly get 0, something like that here.
You'll get a 9.
Yeah.
Positive 9.
A positive 9, right? You get a positive 9. So now, guys, look at this image. If you look at this result,
At the same pixel width and pixel height in the convoluted image also, do we have to, create borders on both height and width?
we'll come to that. We'll come to that. Hold that. Hold that. So what happens, guys, is if you do that, some things begin to stand out. Do you notice that
Can you scroll a little up?
Yes. Right? And by the way, there may be some little mistakes here. So one thing you notice that all of these are vastly negative numbers relative to this column, isn't it? So if you were to actually attach colors to this, right, you will notice that you will get a band which is like this, dark and sort of gray, maybe gray, neutral, positive. Right? So what happens is that, but this band will show through. Right? You will see that this is a rather dark band. And what you're detecting is an edge. And if I had not, if I had done like a simpler version, like if I had put a 9 here and 9 here and 9 here. In other words, if I had made it very sharp, these values would be even more extreme. You can play around with it and you can see that if you try to paint this, the result, the convolutional result, what you have detected is a sharp contrast as you go in this direction. In other words, you have detected a vertical edge. Right? So do this, guys, a simpler version. I shouldn't have stuck in the diagonal. Suppose you have this. Huh? You have 1, 2, 3, 4. 1, 2, 3, 4. And suppose you have a strong edge, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 9, 9, 9, 9, 9. And see what happens when you convolute this with this filter, the way that we did as a practice thing. This will be 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1. Just see what does it produce. Do we want to go through the simpler exercise all over again and see what it produces? Let's do that. So this, when applied to this region, the first column produces 0, second column produces 0, third column produces minus 27, right? Then you move the filter one step below, minus 27, minus 27. Now you move this filter across to this place, and what you get is, like suppose you have your filter like this, you multiply this, so you will get only this part. Again, minus 27, minus 27. That's what I seem to be getting. Correct me, guys, if you see something differently. Yeah, minus 27, minus 27. And then you move it one more step. You come here, third step, you get 999, that is plus 27, 0 and minus 27. So you get 0, 0, 0. Do you see that, guys? Huh? So you end up with this. So when you do this, like do it in such a clear way, do you see that the edge is immediately visible? If you were to paint it, giving these color values, any kind of a image renderer will make this black, absolutely black, or very negative, and this as a different lighter. Let me not call it black, but let me call it darker.
Can you scroll up a little bit?
So guys, what is happening? You guys are not seeing the full image, or what's happening? The full screen in the picture, in your screens?
No, just one line is all that's going. See if it's not.
See the grids.
So you see that you see a vertical, horizontal, the vertical edge. So if you look at the history of the computer vision community, people have thought a lot about these filters. There are filters, this detects a vertical line. Another thing can detect horizontal lines. You know, if you do the filter 1, 1, 1, 0, 0, 0, right? And this is a 3 by 3 filter, right? You can have filters of different sizes. Typically you take an odd number times odd number. You can apply this filter, and if there are any horizontal lines, you can detect. So why does it matter to be able to detect those lines? So suppose you have a picture, you have a house. what happens? A vertical fictor, vertical edge detector will go, let me call the vertical edge detector, it will go and detect all of these lines. Would you agree? These lines in the image. And then a horizontal line detector will come and it will detect all of these lines. And then let's say that you have a diagonal line detector, it will go and detect these lines. You see what it is all leading up to? That between the three filters, the horizontal edge detector will detect some features, vertical edge features. The horizontal edge detector will detect all of these features, the green features, and the diagonal edge detector will detect the basically the slant of the house, the roof. But between the three of them, in some sense, you can logically think that they have pretty much captured this picture, captured the image or the essence of the image. They at least have the specific ingredients. And so you can say that if I could feed this into some classifier, all of these features, detected features, you could feed into somehow into a classifier. You could be able to tell that this is a house and not a dog. Are you getting some sort of a general sense of where we are proceeding?
Yes.
So
Yes.
that is the main idea. But here comes the beautiful thing. You don't do it at one stroke. What you do is something quite interesting. And I'll just make block diagrams before we get into the nitty-gritties. So suppose you have an image. Now image typically comes with, image comes with, I represent the image in this way, input. Right? The reason is there is the RGB channel, the three here, and then image is whatever. Let's say that your image is, even to be modest, 32 pixel by 32 pixel, right? Suppose you do that, then you realize that your image is actually a three-dimensional object, if you think of it as that, because there'll be a grid of numbers here, and then there'll be grid of numbers here, right? It's a cube of numbers. What happens is that you take filters. You take one filter, let me call it vertical edge, another filter called horizontal edge, another filter called diagonal, and then you can create more and more filters. These are all filters, right? This, and each may detect its own little piece. So what have they done? They have, when you produce this output, the convolutional, they have done primitive geometric detection, or geometric primitives they have detected, the other way around. Geometric primitives, little edges, little diagonals, primitives. So it's just a fancy word of saying these little pieces, the little edge, the little corner, the little that detection. It has detected that, right? This is the lowest level features you can do, a very low level or detailed feature detection. It has done. So now what you do is you repeat it. You imagine that these little primitives, they feed into another layer of filters, convolutional filters, con layer. And what it does is maybe it recognizes a box, right? There is one filter that will tell you that is there a box. Another filter, and I'm just making it up, another filter will tell you whether you have this. Another filter will tell you whether you have a circle, right? Because cats will have circles, right? Things like that. So it will tell you, and those detections feed into a higher level of abstraction. And ultimately you go a few layers, and what you see is that the layers, many layers later of convolution later, one of them is clearly forming a picture of a house, right? Things like that. Are we together? Or another one, if it sees a cat, it's forming a picture of a cat and things like that. So if it is a house, then all of these filters, they will all begin to agree with each other. They will all be recognizing the house in some way or the other. Right? They'll begin to do that because they will all begin to put literally the word is put the pieces together. Very much like if you think back to the cat and the brain of the cat, what is the cat doing? We believe, we don't really know how we see, but the belief is that in a very rough sense, the external object, the external world projects a sort of an image as though on an internal screen, this a bunch of filters. And then our cat brain or our human brain, it sort of puts it together, puts the pieces together and constructs recognition of what it is. Right? In the same way, we are doing it here. So when we do it here, there's a nice term for that. It is called representation learning. It's a very important term. And in a way, it's a better term for deep neural networks. Representation learning. Representation learning. And in many ways, a lot of people prefer that instead of calling it deep learning, this subject, it should be called representation learning. And the main idea of this representation learning is that as you don't do all of learning in one shot. So imagine that you had just a logistic regression model. Input goes out and output, you have to tell whether it's a cat or dog, right? Or a cat or a house. You don't have a choice. You can't do systematic learning of primitives, then higher order features, then higher order features, and so on and so forth. But if you do things like that in convolutionals, what you're doing is you're first picking up basic geometric primitives, then you're taking next order primitives, next order and the next order and the next order. Now what I've done on your website is I've put some couple of sites and resources on convolutional nets. You can see this in a very visual way, how a neural network is recognizing that. Right? Now there is a little bit of a mathematics of basic arithmetic, that if I start out with a filter like n by n cross number of channels, by the way, number of colors is called number of channels, right? Initial input is this. Suppose I start with filters. So what is the filter size is typically written as f. How many filters I have in the, so this you would call the 0th layer, the input layer. This you would call the first layer, remember? And then you would have a second layer. So in the world of neural networks, you would say that, let's say that the filter is 3 by 3. If I say F3, it means it's 3 cross 3 filter, right? Now, how many filters I have? This is the N1. So I may choose to have a certain number of filters. The minimum number of filters that I need, how many filters would I need? Input, right? So each of these filters, by the way, has to be 3D. Why? Because it has to match the input channel. But I can have lots of filters, lots of these filters matching the dimensions, the channel dimensions of that input. And I can have this. So N1 could be anything. Let's say that N1 is equal to 10, right? And so your N times N, and usually what happens is as you scan, there are a couple of nuances or extra bits you can do. What you can do is, if you look at this picture, 5 by 5, let me just take 4 by 4. Suppose you put, or maybe let's make it 5 by 5. Suppose you took a 3 by 3 filter. So now this filter, as it moves in this direction, you realize that this guy, it was visited only once, but this guy will be visited twice. This guy will be visited thrice, 3 times over. Do you see that, guys? Right? And this guy would be visited 6 times because it would also be visited in the downwards journey. And this guy will be visited 9 times, right? So what happens is that you visit different pixels a different number of times, which is not good because suppose something very crucial is there on the edge, you may miss it. So what people do is that they go and pad it. They will say, for example, that suppose I were to pad it by 2. and fill it with some numbers. Right? Just maybe fill it with zeros. I extend it and then the image in mathematically and just pad it, just go stick zeros into it. Zeros. And so now you have to start your filter from here, this one. You have to start your filter from here and you have to skip. And so all the elements would be equally visited, right? Or at least better visited. When you do that, you are, the process is called padding. So when you do filters and you use filters, you typically specify how much is your padding, usually determined by this padding, right? So there are two kinds of paddings that people use. One is called valid padding. Valid padding says that because we really don't know what the value outside would be, so we are not going to guess. We are just going to say padding is equal to 0. In other words, no padding, right? When you do no padding, then your image shrinks. You know, the next layer image, this, the output of this, when you convolute this, you will end up with new images, new things, which will be smaller for valid padding or absence. And then there is another padding called the same padding. These are little technical details, guys. You don't have to remember it, because you just, as you do, it comes almost by osmosis. The osmosis, this padding says that you need to pad in such a way that it is the size of the input and the output remains the same. This layer, the layer 1 size, the first layer size, the output. So these are filters.
Could you please scroll up?
The first layer size is exactly the same as the input size. The size is preserved, right? So input and output of the filter con is the same. That is why it is called same padding. In same padding, they are preserved. All right, and give me a second.
I have a question.
Yes.
How does the number of channels, the RGB colors, map into the filters? That I didn't
So what
understand.
happens is that each of your filters, remember I just do it as a two-dimensional object, but it is actually three-dimensional. It is the, let's say this is 3 cross 3, but how many channels are there? Let us say that there are 3 channels. Then here there's a third dimension, 3, also here.
I see.
That's all it is. So you're applying a three-dimensional volumetric, you're matching, see this is a volume, right, in this beginning place. So you're matching that whole volume. Filter is a volume because your input is a volume. Okay? So it is volumetric matching. Matching. That's all it is. It's nothing mysterious about it. But then how many filters you have here in the first layer, that is totally your choice. Okay? So that is the concept of padding. Then there is also the concept of stride. Right? And it also adds another degree of flexibility. Like what it says is that when I slide the filter forward, do I need to just move 1 step or can I jump 2 step or 3 step? So that is called the amount of jump while moving the filter. Are we together? That's all it is. How much should I move? Right? By the way, the same padding, right? There is a simple expression. The amount of padding that you should give is the size of the filter minus 1 over 2. If you give this, yeah, and typically you take filters as odd numbers, so minus 1 will be even, and so even will divide nicely with 2, even will divide nicely with 2, and so this quantity will come out as a nice round number, nice integer. Right? Typically, it will be 1, 2, 3, 4, whatever it is. If, for example, if you take a filter 5 by 5, so 5 minus 1 is 4, divided by 2 is 2. So your padding is 2. Are we getting the idea, guys? Right? So that is it. Now, stride is typically written as S. In the literature, everywhere you'll notice that the letter S is reserved for stride. Right? It is literally how much you jump. So, for example, you have a situation like this. Right? So suppose you have a 3 by 3 filter. Let me just give it here, a 3 by 3 filter. Suppose your S is equal to 2. Then what it means is the next will not be here. The next will be here. Do you see? This edge jumped to this edge. It jumped 2 steps. Okay? So that is the stride. And so you can play with different strides and so on and so forth. Then the question comes that suppose I choose a certain filter. So at any given layer, let's design a neural network. Suppose I have an input. Input is n cross n image size. Let's say 32 cross 32. I'll take a question in a minute. Cross number of channels. Let's say 3 RGB. Right? So suppose this is it. This is your input. And suppose you create a filter of size f, filter f, which is f cross f, right? You can say 5 cross 5 or whatever it is that you want to do. Typically, you start with small filters. Let's say 3 cross 3, and then your padding is P, and your stride is S, and the number of channels that you have, the number of filters that you have in the first layer is whatever you want it to be. So the question is, what is the output? If you apply this filter and go over this image, what comes out? Right? What is the output? The output of this will again be, a grid, a 3-dimensional grid. So now what happens is, this will be of size of this will be, there's a formula here. You can convince yourself that this is true. I'll just write it here. And you take the floor notation. In other words, if it comes out to be 3.6, keep it 3. Okay? So that will end up being the size, the new size of the, the output. So that's how it goes, guys. The size depends on this. Right? You can work it out. Like, for example, in our case, we started out with, let's go back and see whether this matches or not. Right? We started out with 5. This was 5 cross 5. This was 3 cross 3. So let's work it out. When you do 5, n is equal to 5. If you go back to the formula, the n is equal to 5, right? P is equal to 1. We took P is equal to 1. The stride is equal to 1. So what does our thing say now? What does it say? N plus 2P minus F over stride plus 1, right? Ceiling of it. Let's see. 5 padding is, well, let's say that we didn't give any padding. So here padding was 0 because we didn't pad when we were doing this. Plus 0 minus 3 divided by stride was 1 plus 1. So what does it come to? 2 plus 1 is equal to 3. Is that correct? This is 3 plus. Now you can look at this image and tell that it is indeed 3 by 3. Do you see that, guys? That the output, you could tell using the formula that this is what it will come out to be. And that formula is just common sense. If you just think about it, that is exactly what you'll come out with. Okay. So now comes an interesting thought. And that's, so far you may say, okay, where is the neural networks? Where is the machine learning? And in fact, there is no machine learning in what we have done so far. Now let's bring the machine learning in. The machine learning comes with this interesting thought. How do you design good filters? You know, you can say, I will have a vertical edge detector, I'll have a horizontal edge detector, diagonal detector, and so forth. But see, in a given image, suppose there are no horizontal edges. For whatever reason, there are no horizontal edges. Then your horizontal edge filter is thoroughly useless, right? In the same way, if there are no diagonals, your diagonal filter will be useless. So a lot of your filter will go useless if you hand design it, which is what used to happen. Then comes an interesting thought. At each layer, so what happens is when you apply a filter, what do? You take a filter, which is, let's take this weight, 3x3 filter. Huh? Let's just call this weight W1, W2, W3, W4, W5, W6, W7, W8, W9, right? And this is just your filter 1, F1. You can have another F2, right? Am I doing it right? Yes. And then F3, more filters. And each of these, they can have, let me say W1, maybe 1, 1, 1, 1, 1, 1, 1, 1, 1. And this could be W1, 2, W2, 2, W3, 2, and so forth. You get the idea, right? These are different weights. And now you can ask this question, that ultimately what we are trying to do is do a classification. Let's say we are trying to tell whether this is a house or a dog or a cat. So why can we not use a loss function and back propagate and learn the losses? So in other words, can we learn the optimal filters for a problem, to solve a problem by learning in the backprop gradient descent sense. You know, all that we have been learning so far. Can we do this? Gradient descent step. Right? And the answer to that is actually, that is the breakthrough. That's what makes it into a problem in deep learning. So what you do is typically you go like this. You take the input image, you put a conv layer. Let me just put it as a conv layer, made up of so many filters. And I'll just write it as this, NC, N1 filters. Each of them are F cross F or whatever it is. So this goes in. So this is the conv 1 layer. You get the output. This is your Z, this output that you produced. So in other words, going back up to our story, this thing in the language of machine learning, this thing that we produced, this is the Z, this is the input X, this is the filter. Think of it, this is your weight vector, because now remember that we are saying that these are weights that have to be learned. Would you agree that Z is essentially X convoluted with W? It's almost the same thing, the inner product. Z is this. You see how the ideas come together, guys? This is
Yes.
Z. And it is literally the convolution. This convolution is the inner product, right? In some sense, in a convolutional sense, not a direct inner product because these matrices are not matched. But in the convolutional sense, if you convolate it, it's not the inner product, it's sort of a convoluted inner product, but it is as close as you can get to inner product. And now this begins to sing, you know, we are already familiar with this whole notation that Z is equal to, in the dense neural networks, we were doing this all the time, W dot X, remember, to produce Z, the inner product of this. Now the only difference there, so this was for a dense net, dense layers. Now the only difference is that we are changing the vocabulary and we are saying Z is W convolation X. Okay? This is the convolation symbol. conv symbol. Are we together? It looks uncannily similar. So what do we do to Z? Do you remember what do we do to Z? Z goes and gets what? Distorted using an activation function. Do we remember that, guys? Remember that a traditional and perceptron was this, right? The weights go in X, Z, Z is equal to W dot X. And then there is a distortion function, activation of Z, right? This output is the some activation function applied to Z. Do we remember this, guys?
Yes.
By now it should be familiar. So let's do exactly that. You take the Z and you apply some activation function. I'm putting sigma here just to say activation function. So let's say that you produce an output, A of Z, let's say, AZ, right? Apply an activation function. Are we together? You apply the activation function here. And so this together almost makes, actually there's something else called padding, another pooling, a max pooling, and there is also something called average pooling, which we don't use very much these days, but max pooling. There is something, so I've sort of glossed over something. But this part, a convolutional layer, is made up of this. So let me write it this way. One conv layer, just like you have a dense hidden layer in a dense net, one conv layer is made up of A, the filters and convolution with it, convolution with it of the input, previous layer's output. B, activation function applied. And this looks very simple. X becomes weight convoluted with X, convoluted with X input, and this, that leads to Z is equal to this, right? And then this is just applying some activation function of Z. If you remember, that's what you were doing in the dense-net also. Very similar. Now there is one more thing that I glossed over that people do after this, after the activation, or this, or before the activation. They do one. It's actually after the activation. They do one more thing. They apply the max pooling. Max pooling is very interesting. It is like is this. So let me take this example. Suppose you have numbers. Let me take this numbers. I'll take a 4 by 4 grid. 1, 4, 0, 2. Right? And 5, 2, 3, 9. 1, 4, 8, 2. And 1, 1, 7, 2. Like I'll just randomly throw in some numbers for no better reason. What you do is you take a window. Let's say you take a window, and this is a common window, 2 by 2 window. And you frame that window on top of this. When you frame it on top of this, now you look into the window and say, which is the biggest value? Okay. So here the biggest value is, what is the biggest value here in this window, yellow window, guys?
4. 4.
4. So you write 4 here. Then you go to you take the window here and you ask in this window, what is the biggest value? 9, right? Then in this window, what's the biggest value? 8. And in this window, what's the biggest value? 7. And you say that if I do max pooling, this operation is called max pooling. For historic reason, means you pick up the maximum. In the olden days, what people used to do is that they would take the average. it was much more common to do average. Still, somebody noticed that you take the max is actually works better. So the way people justify max is, here is one intuition I'll give you for max. It is that, see, think of each of these numbers as a vote for a vertical edge. Suppose a filter is that filter is checking for vertical edge. Each of these numbers is saying around here I see a vertical edge. So when you put a window like this and you take the maximum vote, you're saying how confident in this region are you that there is a vertical edge here, here. Do you see what I mean by that, guys? Yeah. So that is the intuition that you think of it as a maximum vote in that neighborhood. So it's like you're in the forest and some of you see tigers or see an animal, right? One says it's a deer, another says no, it's not a deer, it's an antelope. Another says it's a tiger. Now, all things said, who are you likely to take more seriously? Or what can have the most consequence? You'd say, well, I'm safer if I believe it's a tiger. I don't know, it's just a hand-waving argument. It's not very persuasive, but something like that. Actually, the honest truth is that why max pooling works as an extra step in the convolution, nobody really knows. We are just guessing. We're just throwing sort of heuristic arguments or post hoc reasoning. But the fact of the matter is, we have found that if in the one conv layer, you put max pooling at the end of it, it just leads to stronger signal. It just leads to better results. So these three things make up of it. You convolate with filters, you activate it, use activation functions, you max pool it and so forth, right? So you do all of that. Then all three things you do. Then, so now what you can do is you can have just as, and typically in the literature, you'll notice that convolution layers are typically represented as solid cubes, rectangular cubes or something. So output of this, one conv one will go into the next conv layer, right? Will go into next conv layer, conv 2. So whenever you see these diagrams, remember that it includes all of this: convolation, activation, pooling. Right? Actually, I might have gotten the order of these two reversed. Okay, so you do that. And so, for example, one of the old architectures is LeNet, right? Now, LeNet 5, and I'll come to that. But one rule is there. As you convolate and move forward, here are some rules. Successive conv layers should have decreasing size and increasing number of filters. Number of filters. And number of filters people also call number of channels. This really should scroll up. Number of channels. So why number of channels increases and is the idea is that you're hoping that you're recognizing more and more things. Each filter is recognizing something. So as you learn more and more in different layers, hopefully you're discovering more and more features that are present in the image. That's why you try to increase the number of filters and it works really well, right? But the size of all of these, each of the layers, it decreases. The idea is that now you're discovering higher order things, right? In different places. So that is that. And when you do that, at the end of it, let's say connet, right? So at the end of it, suppose you end up with, I don't know what in this particular case we end up with, but let me just guess that you end up with 17 cross 17 cross, let's say that you have 20 layers, something like this. So you realize that this is a pretty large number, isn't it? 17 cross 17 is the size of it, and there are 20 filters or channels there. So then what you do, this result, you can flatten into you do a flattening operation. You can flatten into a single vector. Why? You start reading it like this, and then layer by layer you read it, and you lay it out, and you will get a single flat vector, right? Let me just call this flat vector F vector. Do you agree, guys? You know, you can take this three-dimensional a box of numbers, cube of numbers, and you can flatten it into just one long vector of numbers. So that is called the flattening layer. This is a layer in itself. And then once it is flat, remember that this is beginning to look like the X input of dense layers or fully connected layers, fully connected layers. So technically, you can just suppose you're trying to distinguish between a cat and a house. You can use your softmax right here with obviously size 2, dimension 2. One will try to detect a cat, another will try to detect a house, right? And you could feed all of this flatten directly into it because you're used to that theory by now. But what people do typically is they put some intermediate dense layers, fully connected layers, FC1, FC2 in between, and then they put the softmax layer, right? So overall, to summarize, you have an architecture that looks like this. You have some, these are usually represented as cubes. There goes to another little cube, which is smaller in size, but deeper, right? Which goes to another cube, which is even smaller in size, but really deep, lots and lots of channels. And this goes into a flattening layer. And flattening goes into some fully connected layers, FC1, then FC2. And then let's say that you have a softmax for classification. Does this make sense, guys? And so this sort of picture, they are iconic. You find it very often. The moment you talk about convolutional neural nets or image classification, object detection. So what is object detection? You're looking at a scene. It's a picture. You have to identify all the objects in it. And it is of paramount importance, you know, when you're driving, when you're trying to do a self-driven car, it is very important that the camera, the image that comes from the camera, the AI system is immediately able to recognize a pedestrian who is there in the middle of the road, isn't it? Or some obstruction that's there, a car that's in front of you, and things like that. So for all of those things, this is your basic architecture, right? For object detection, image classification, cats and dogs, or cats and house here. And so remember that in the very first class, we dealt with a couple of architectures. We talked about AlexNet, VGG. Do you guys remember that? The very first lab we did, we tried out many architectures on the ImageNet dataset.
Right.
Right? And then I asked you to just try, or then we tried the CFAR also. And I said that, see, just put your own cat or dog there and see how well it detects in the ImageNet. It's able to do that. Right? So those architectures that are there, they all look like this, except that their convolutional layers are not just one or two layers there. This is, by the way, what I just put is almost the same as a famous and old classic architecture called LeNet 5. That's what it is. Two convolution layers from the input, and then flattening and two dense layers. Right? So, and then the softmax is the final layer. And flattening, you don't call it a layer, you just call it an operation. So that used to be the LeNet 5 and so forth. Very successful actually in its days. So, but now we live in the world of VGG and AlexNet and ResNet. And ResNet, as we just saw in the visualization, we are looking at ResNet 56 and ResNet 101. Those numbers tell about how many layers there are in this. And most of those layers are confidence. Now, I would like to end at this moment the theory part. By the way, guys, all of this will become very real when we do the lab. But at this moment, I'm just putting the ideas here. One more thing. We have a whole month that we will give to this topic. So today, as you can see, I'm skimming. I'm just introducing the basic concepts. The reason is this is it in one theory session. I'm giving you a flavor of it so that I can get you started with the lab. But later on, we'll have one whole month to convolutional neural nets, and we'll do it really deeply, both from a practice and from a theory perspective. We'll redo everything that we talked, but we are just planting seeds in your mind at this moment. Think of it that if you're somewhat familiar or you get the basic high points or ideas, then later on it will become much easier to learn. Are we together, guys? So it raises one question. So why use conv nets at all? Why can't I just use dense nets? Right? Those dense layers. Would anybody like to take a stab at that? A hint, I'll put something in front of you that should be a hint. Let me see, let me go back up, let's see. Yes, look at how dense nets work and see if that tells you something.
CN is much more efficient as, you know, building structure.
In what way is it more efficient?
Uh,
What's that?
yeah,
See, look at it, guys. DenseNet has so many parameters. Just the first layer itself had 200, like close to 200 million parameters, right? That kind of, and then imagine if you created 4 hidden layers or 5 hidden layers, you will be looking at billions of parameters, isn't it? It is extremely hard to train a neural network like that with so many parameters unless you have ginormous amounts of data. It is not feasible, or like Jenny says, you use the word inefficient. So inefficient in that sense. Right? In contrast, let us see how many parameters are there in a filter. Let's go back and look at it. So you're saying that 3 by 3 is a filter. So you have how many parameters are there? 9, just 9 parameters, isn't it? Like the basic idea is you make this filter that you apply, it has just 9 parameters. And so suppose you add the RGB, the 3 color dimensions, it becomes, well, 9 times 3, 27 parameters. And let us say that you have 10 filters that you start out with, which is a good number to start out with. Start with 10 and keep growing the number of parameters, 10 to 20 to 40 or whatever it is. Number of filters. So let's say that the first layer has 10 filters. So now you have 27 weights per filter and 10 filters. So how many total weights do you have, guys? 270, isn't it? 27 times 10. Plus, if you add bias term to each of the filters, if you add a bias term, then another 27. So you have 270 plus 27, right? Not a big deal, under 300. Compare under 300 to 200 million. Do you see the contrast, the tremendous difference? Yeah. 300 parameters are easily trainable, but training 200 million parameters per layer is hopeless almost. Is that coming across, guys? And that's the basic idea. So people say that why is that? Why is this more efficient? Because the same weights we use and slide all over the image, right? So this is variously called by 2 names. People call it spatial invariance. Means the same weight you're sliding all over the image spatially to recognize edges wherever it is, yeah, in a given filter. So you have spatial invariance that gives you. Some people also call it weight sharing and all these ideas. But all it simply means is you don't change the filter when you're computing in the forward direction. You just move the filter, slide the filter around, yeah, all over the image. And the weights remain the same. Because weights remain the same, the number of weights are fairly limited, up to 300, right, per layer. So what happens is that in an architecture like LeanNet, etc., remarkably, most of the learning takes place here. Most learning takes place here in the convolutional layers, right? But in the end, you flatten and people add a couple of dense layers just to catch the non-linearities in the data, right? Before making a softmax prediction. And it turns out that most learning happens here in some sense, and most parameters exist here. Because even with two dense layers, even if you take the dense layers to be, let me say, 512 and 128 or something like that, you realize that still there are lots of parameters sitting there. Most parameters here. You'll still acquire in millions, right, of parameters in your dense layers. And that literally contrasts the efficiency of the convolutional layers versus the dense layers. All right, guys, so I'll recap what we learned, and then I'll take questions. What we learned is that convolution, the idea was derived from studying the fact that different regions of a cat's brain are observing different parts of the scene, right? And so they're lighting up at different parts of the scene. Now you put that fact together with the mathematical notion of convolution. By the way, this is, as I said, mathematically, I'm being a little bit sloppy. People would call it slightly differently, but that's all right. We won't get into that. If you multiply this with this, it's like shining a light into different areas. As you slide your GX horizontally, we are sliding lights at different areas of the curve, and different areas of the curve get illuminated, essentially. That is convolution. And that is exactly what we do with this sort of a torch, which more commonly is called a filter or a kernel. When you shine it upon certain area of the image, you get to know what is there. If there is an edge hiding here, if it is an edge filter, it will shine the light on any edge that may be present there. It will detect the edge. Right? And then you move on to other places. So that's what it does. A filter is like a stencil, cutout stencil. It's looking for specific things. But then comes the question, how do you know which things to look for and not look for? And that's where you say, hey, you know what? Let the machine learn what the best filters are, what the important features are that you should look for, right? By making all of these weights learnable in a machine learning sense, in a deep learning sense, let it be learned through back propagation and gradient descent. Right? And so then you have the concept of representation learning. What you say is that the first layer, let it say it picks up little edges. By the way, we'll see these things in a very visual way in the lab. Huh? But at this moment, let's stay with the theory. So it will pick up little edges. The next layer will learn from those little primitives and maybe make bigger primitives, squares and things like that. And the next layer will do something else. And by the time you reach the last layer, if it is a cat, you will notice that the filters downstream, and there are lots of filters, they all are beginning to say cat, 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 cat. Right? And so it begins to get very clear that from many perspectives, each sort of filter in the later layer is learning in a different way, and think about it in some sense that they're coming to the same conclusion. They're reinforcing each other. They're saying it's a cat, right? And maybe I'll take a moment to show you a visualization of it. That would be a good way to end. That's hierarchical learning, and the rest of it are technical details, like how do you keep increasing the number of filters, decreasing the size, and create an architecture. Don't forget to do max pooling. Those are minor details. So long as you get the concept, those details you can pick up. But I would like to end by showing you something. And again, guys, all of these resources are there on your web page, in your course page. I again encourage you to look into that. So in the fund resources, where are the fund resources? experiments, depart, embedded projectors, visualizing high. Okay, let's try this one. I think this one has something. By the way, this is basic JavaScript. You can use it to detect things. Oh, let's play around with how things work. Classify. See, you have this image, input image, right? And it is trying to detect what it is. Go here and play with it. You'll see how, so just pay attention to this, guys. I wish I could stop it. Let me see if there's a stop button. Pause. Let me pause it. Okay, guys, look at this. When you look at the activation, guys, the input is this, right? When you look at the convolution layers, can you see some aspects of the horse showing up? Guys, do you think these filters are telling you that it might be a horse?
Right. Yes.
It is saying that, isn't it? So it is, then you pull it, and now you go to the next layer. Do you notice that the number of filters increases? Right? And it keeps going like that, right? So you start out with basically primitives, right? And then finally, what happens is, as you go down, you do a fully connected layer, and then you're trying to tell one of 10 objects. What are the 10 objects? These are the objects that it is trying to tell, right? So then it will come to the conclusion that this picture, for example, is neither a deer nor a truck nor a cat, right? And this picture is, a horse. How much of a horse it is, or this one is likely to be a truck. Green is, it is good identification, right? So you get this, play with these pictures, guys, and the code is very simple. This is the beauty of it. You can take this JavaScript code, very useful, the ConvNet library. Do you realize that you just need to add, literally you can write it in a HTML file and run it. If you know basic HTML, you can do that. You can even change the network, and you can add your own. So for example, do you know, you can go and change this is a filter. Let's see if you understand it. Input is 32 by 32 and 3 colors. This is, by the way, the famous ImageNet dataset. So now let's look at here. Convolution layers, type convolution. What is it saying? This size is 5, right? What is the size of what? Size of filter. It's right. It's 5, and then filter size in convolutions are always odd. How many filters you having in the first layer? 16. Then stride is 1, padding is 2. Why do we have padding 2? Because it will keep the size the same. Right? It's a size preserving thing. So in the next layer, again, you use a filter size 1, 5 by 5 filter, but you have 20 filters. Stride 1, padding 2. Likewise, against filter 5, number of filters is, they haven't increased, 20, and go change it, just go change it and see how it affects your recognition. And then, as you can imagine, you create the net and you just train the net. Yeah. This code, without even knowing JavaScript, I hope this code is looking fairly obvious to understand, right? And you can literally see how these filters are detecting little things, right? Given the input, how they're going about doing their jobs. So that's it. I'll end today with that. Any questions, guys? And there are many visualizations of the inner layers. I think on the web page, I can't see the exact location. I have put many of those things here. Another of them is neural network paints an image. Let's look at this. How does it, the same, this is your net. This is funny, of course, just using a dense net. It is trying to get a picture of the cat, right? It's trying to gradually make the picture. And I don't know if you can see that this picture on the right is gradually beginning to look like the picture on the left. So you can play with different pictures and so forth. These are different demos. You can play with that. And This is the MNIST data. We will deal with it in the lab. So you give it a data and you see how it is recognizing. Look at this. I wish I can pause it somewhere. Where is the pause button? Pause. Let's pause somewhere. Do you see that 0 is the input? And how each of the filters in their own different ways, they're recognizing this.
Yes.
Right? They all are coming to a similar conclusion, right? And then after the ReLU, this is the activation, the gradients, and so on and so forth. And you go to the next layer and the next layer and so forth. So that is convolution. This is a new architecture we learned besides the feed-forward network. These are called convolutional neural nets. It turns out that once you become familiar with all these little bits of mechanics, that is all there is to convolutional neural nets. Architecturally, they are very simple and they're insanely effective for any kind of spatial recognition, like image is a spatial object, any kind of spatial recognition, spatial classification, convolutions do marvelously. All right, guys. And so then I'll stop the recording and take questions.